Welcome to a lesson on solving for time in the annuity and loan formulas using common logarithms. This lesson does assume you've already watched the video on how to solve exponential equations using common logarithms. Often, we are interested in how long it will take to accumulate money or how long we need to extend a loan to bring payments down to a reasonable level. This requires solving for time in the annuity or loan formulas, which we see here below. In both cases, capital N is time in years. To solve for n, we'll use logarithms. More specifically, we'll be using common logarithms. In this lesson, we'll be using the annuity formula, and then we'll show how to set up a similar problem using the loan formula. Let's begin by reviewing what the variables represent in the annuity formula. P sub n is the balance in the account after n years. D is the regular deposit, or deposit every time period. R is the annual interest rate as a decimal, and K is the number of compounding periods in 1 year. Let's take a look at our example. If you invest $200 per month in an account that pays 3.5% compounded monthly interest, how long will it take for the account to grow to $12,000? Let's begin by listing out the given information. If you're investing $200 per month, that means that D is 200. The interest rate is 3.5%. As a decimal, that would be 0.035, which is R. Interest is compounded monthly, and since there are 12 months in a year, K is 12. We want to know how long it will take for the account to grow to $12,000, so P sub n would be 12,000. We don't know the time, so we're trying to solve for n. And now we'll sub these values into our equation and then solve for n. So notice that D is equal to 200, K is equal to 12, which occurs here, here, and here. R is equal to 0.035, which is here and here. And P sub n is equal to 12,000. So again, our goal here is to solve this for n, and because n is in the exponent, this is why we need logarithms to solve this equation. Now to begin, notice how we have this fraction here in the denominator, and this fraction bar means division. So notice how if we multiply both sides of the equation by this fraction here, we can eliminate this fraction from the right side. Again, in this first step, we multiplied both sides of the equation by this fraction here. If it's helpful, we can think of this as being over 1, and therefore these two simplify to 1. And this fraction times 12,000 equals 35. Let's just verify that. We have 0.035 divided by 12, and then times 12,000. So that's where the 35 came from. Now for the next step, this is 200 times this quantity here. So let's go ahead and divide both sides by 200, which means this will simplify to 1, so we can drop these out of parentheses, and we'll leave this as a fraction even though we could simplify it. So now we have 35 divided by 200 equals this quantity here. Again, notice how this is raised to the 12n power. So for the next step, we will add 1 to both sides. So we'd have 35 200ths plus 1. Again, we could try to simplify this, but I'm not going to. And this is equal to the quantity 1 plus 0.035 divided by 12 raised to the power of 12n. This is where the common log is going to help us solve this. Let's go ahead and put this in parentheses too. We're going to take the common log of both sides of the equation. By doing this, we can apply the power property of logarithms here, meaning we can take the exponent of 12n and move it to the front. So we'd have 12n times this logarithm. So now we have log of 35 divided by 200 plus 1 equals 12n times log of 1 plus 0.035 divided by 12. And now we can actually solve for n. If we want to isolate n, we don't want this 12 here, or this log, which means we can now divide both sides by 12 log of the quantity 1 plus 0.035 divided by 12. And this will give us the value of n. Notice if we simplify the right side, 12 over 12 simplifies to 1, and these two logs are the same, so this also simplifies to 1. Now we could have converted some of this to decimals earlier, but then if we use rounded decimals to perform more calculations, our answer would not be as accurate. So now on the right side we just have n, and to evaluate the left side we'll go back to the calculator. We do want to put the entire numerator and denominator in its own set of parentheses, so we'll have an open parenthesis, common log, which is here, and then we have 35 divided by 200 plus 1. Now we need a closed parenthesis for the logarithm, then another closed parenthesis for the numerator, and then divided by, open parenthesis for the denominator, 12 common log 1 plus 0.035 divided by 12, close parenthesis for the logarithm, another close parenthesis for the denominator, and enter. So if we round to the nearest tenth, we can say this would take approximately 4.6 years. So again, this means that if you invest $200 per month in an account that pays 3.5% compounded monthly interest, in approximately 4.6 years, the balance would be approximately $12,000. Now this example was for an annuity, but the process would be the same if we used a loan formula, even though the equation would look a little bit different. So before we go, let's at least set one up that involves the loan formula. For example, if you purchase a $799 tablet on your credit card, which has an interest rate of 14% compounded monthly, how long will it take for you to pay off the purchase if you make payments of $75 a month? So using our loan formula this time, notice that P sub 0, or the principal, would be $799. The monthly payment D is $75. The interest rate as a decimal would be 0.14. And because the interest is compounded monthly and there's 12 months in a year, K is 12. So now we can follow the same procedure that we did for the annuity formula and solve this for n to answer the question. I hope you found this helpful.